Today I'll be introducing the discrete choice models. Discrete choice models are a probabilistic model where the customer chooses between a finite set of alternatives, and each alternative is distinct, right? That means discrete. There's no continuous function that we're choosing. We have alternatives indexed by I, and we can say the number of them is big N, and each one has Qi, which is the choice probability, the probability that a random customer chooses alternative I. And so all the customers are identical. And then we have a subset of discrete choice models that's most common is random utility, meaning utility is a function that represents how desirable a certain choice is. And so the highest utility alternative is chosen. Putting that in math notations, right, that means Qi is the probability that I equals the argmax over I of ui, of utility I. It has the maximum utility. Or if it's confusing to use the same index, you could replace this with a k, right? We could also say this is probability ui is greater than uj for all I not equal to j, right? That's an equivalent statement saying that qi is the probability that ui is the highest out of all the u's, right? And specifically, our utility is random, but that means there's still a deterministic component unless it's zero. So we can split the randomness and the deterministic component, right? So here's the mean utility for alternative I that's deterministic, like known as an input to the model. And then here's the random component, and the distribution of this is an assumption of the model, but depending on the type of random utility model, you can choose different apps I. For example, let's choose a simple apps I. We could have it equal to 4, 0, or negative 4 with probability 0.5, 0.2, 0.3, and let's say that mu equals 1, 4, and 7. So that means mu1 is the mean utility that a customer chooses product 1, and the mean utility that a customer chooses product 3 is 7. So it's much more likely that product 3 is chosen than product 1, right? But because of this EPS having a high variation, product 3 is not going to be chosen every time. There is a positive probability that product 1 is chosen, and that's Q1, and we can compute, right? So we're going to find the probability that U1 is greater than U2 and U1 is greater than U3. Or in terms of the mu I and eps I, mu1 plus eps1 greater than mu2 plus eps2, mu1 plus eps1 greater than mu3 plus eps3. And remember, this one is 1, this one is 4, this one is 1, this one is 7, substituting these values given up here. And then we can look what is the possible values for eps I, so that eps1 is so big that 1 plus eps1 is greater than 4, and eps2 is so small, right? So if eps1 was 4, eps2 was negative 4, and eps3 was negative 4, then we'd have 1 plus 4 is 5, and 4 minus 4 is 0. So that would work out. The utility 1 would be 5. In other words, utility 1 equals 5. utility 2 equals 0, and utility 3 would be the 7 minus 4, which equals 3, right? And there's another case for the EPS. We would still have to have EPS1 be 4 and EPS3 be negative 4, but EPS2 could be 0, and then we'd have U1 equals 5, U2 equals 4, U3 equals 3. Like, you don't necessarily have to show this much work as long as you get down to this step, right? And then each of the EPS are independent by assumption, and so we can substitute in the probabilities from the PMF given up there. So 0.5 times 0.3 times 0.3 plus 0.5 times 0.2 times 0.3 equals 0.075. And like, see, with a simple function for the PMF, we can easily compute a probability. Even if it's a more complicated distribution, we can easily compute the probability given a certain mu value, right? And so let's move on to one of the more useful EPS distributions, which is given from the multinomial Logit model, right? So there we have EPS-I is a Gumbel 0, 1 distribution, and Gumbel 0, 1, we have f of x equals e to the negative x, e to the negative x. And then we have our CDF, so PDF, CDF, which is the integral. Integral. And then we can find QI is going to be given from this, right? So if we were to choose mu, then we know QI given mu is given by this PDF, right? So that's the probability that mu I plus EPS-I is greater than mu j plus EPS-j for all I not equal to j, just repeating the definition of choice probability. And then we can substitute in this PDF, because that gives us probability of a certain EPS-I value. And then we'll have to deal with all the other EPS-j values. Since that's a little complicated, let's break the notation into two steps, right? So one, we'll just do, or maybe we write the f of x first, probability of getting a certain EPS-I, and then we'd have to multiply that by the probability ui plus EPS-I is greater than mu j plus EPS-j for all I not equal to j, given that EPS-I equals to x dx, right? And so that just means what we're actually, the difficult part is finding this conditional probability, right? And so just taking this out separately, you would have to multiply the probabilities together over all j not equal to I. The probability ui plus EPS-I is greater than mu j plus EPS-j. Does that make sense? Because it's true for all of them, the probability of the intersection is the probability of each individually multiplied out. And pi denotes the product. And then from there, we can, remember we're still given that EPS-I equals to x. So we can just replace EPS-I with x and try to get this more in terms of EPS-j, so that we can use the distribution of EPS-j, which is also known, right? So that's the same as pi over the product over j not equals to I probability eps j is less than or equal to mu I plus x minus mu j, just moving that to the other side and flipping it, right? And we can see that this probability eps j is less than or equal to the value. That's the CDF. And then substitute in the CDF function given above. And then product of something raised to the power of something, we can change that to something to the power of the sum of the powers, right? If we do a to the 2, that's the same as a to the 1 times a to the 1. So right now we have it written in this sort of form, right, where we're multiplying all the terms together. But really, multiplying the terms together is the same as adding up the exponents. So we can do e to the negative, or yeah, you can put the negative on the inside or outside of the summation of j not equal to I, e to the negative mu plus mu I plus x minus mu j. And then we can do the same sort of thing. Like, well, yeah, for simplicity, like let's just take out the e to the negative x, because these are the only parts that are changing with the summation. So each time we're going to be doing e to the negative x. So minus e to the negative x times the summation of j not equal to I of e to the mu j minus mu I. Yeah, that's the right signs. And then we can go back to the whole qi of mu function up here. So remember, this is just taking out this part of the integral. So going back to the full integral, we have integral from infinity to negative infinity f of x. Let's go ahead and substitute in what that f of x is. It's e to the negative x, e to the e to the negative x, and then times this thing, e to the negative x, or like this is all in the exponent. Maybe I should have just done exp notation, but that's okay. Like we only have one more step that we can simplify, and then we'll take the integral. Right, so we have an e to the negative x out front, but then these two we can combine. E to the negative x times 1 plus that summation. Right, we have it once here and then the summation times over there. Like let a equal the summation plus 1 Oh, I lost an exp here. Yeah, e to the mu j minus mu I, e to the mu j minus mu I. Yeah, and then let this equal the summation even mu j minus mu I plus 1, and then we can set y equal to e to the negative x, then dy would be negative e to the negative x dx. And so this whole integral equals the integral from y equals, so we plug in negative infinity, that gives us infinity. We plug in infinity, that gives us 0. And then we have e to the, so this plus this gives us our dy, and then this thing gives us e to the negative ya. And then, because there's this negative sign when we do the dy, right, we actually need a negative up here. And then when we take that integral, that gives us e to the negative ya over a, y equals 0, y equals infinity, and then plug in the 0 for y, and then subtract when you're plugging in the infinity, but when you plug in the infinity, it's just 0, so only the e to the 0, which is 1, over a is our result. And so that's substituting back in what our a is, a good result for our answer, e to the mu j minus mu I plus 1. So basically, qi of mu, we're taking all the other j's, all the other mu except for mu I, and subtracting them by mu I, raising that to the power of e, summing it, and adding to 1. And note, like, this 1 is the same as e to the mu I minus mu I, which would be e to the 0, right? So that really is like the same as doing the summation over all I, e to the mu, or summation over all j, e to the mu j minus mu I. Or yeah, but basically, like, the 1 is representing that itself adds to the total probability. So it's 1 over the probability of all the choices weighted appropriately. Yeah. Oh, and then this, we can, since this EI is the same, this is the same every time, right? That's summation over j, e to the mu j, e to the negative mu I, and then we can bring the mu I up top, summation over j, e to the mu j, and we were saying that goes from 1 to n, or we could have a set of alternatives and say j is a set of that alternatives, whatever notation. But anyways, this is called the softmax function, softmax of mu indexed at I, right? We also denote that by sigma of mu given I. So this function is pretty common in other data models. And yeah, what's so nice about this is the independence of irrelevant alternatives. So comparison of two alternatives I and j only depends on the centers ui and uj, not any other alternatives, right? Because if we take qi of mu and divide by qj of mu, that means we're left with softmax of mu I over softmax of mu j. Looking at this function, this is the same for both, right? So we're just left with e of mu I over e of mu j equals e of mu I minus mu j. Like, so this is called the odds ratio, pretty common in probabilities. We're saying that they're independent because the ratio of them can be found only using mu1, mu I, and mu j. We don't need the other mu's, the other means, right? And so this also implies that adding one alternative decreases the choice probabilities for all the other alternatives proportionately, right? It's not going to disproportionately impact some alternative that is more similar to it. There's no similarity between alternatives. They all are just given by independent utility functions. And then another special case, EI is given by normal 0 sigma. That would mean, or if we just look at all the distributions of F's at once and gave them a capital sigma variance, covariance matrix, then there could be some non-independent F's, right? But either way, this would be called multinomial probit instead of multinomial logic. However, there's no like closed form for the resulting choice probability, right? So you'd have to compute it through simulation. The other nice feature about the multinomial logic is we can look at a subset of choices. Sometimes not all the alternatives are available. So if a subset S exists N, where N is set of all alternatives, then the choice probability, then Qi, like given S. So like we could write that as a function of mu and S, or like we could put them in the subscript, whatever. It's gonna be positive if this I is in S, and it's 0 if I is not in S. And what value is it going to be? Well, it's going to be e to the mu I over the sum of j in S. Instead of looking at all the j's, just the j's that are in this subset, e to the mu j. Next, let's consider the nested Logit model, where adding an alternative affects alternatives that are similar to it more than it does other alternatives, right? So we're going to split our set of alternatives into different nests. It's just a synonym for group or cluster or partition of alternatives. So let's say alternative I, which we said was between 1 to big N and we denoted that set as big N, belongs to one nest little k, which is between 1 and big K, or we could just call this set big K, or maybe we give it curly K like a cap. And then the alternative is chosen first by choosing the corresponding nest, and then the alternative. So the customer decides what category of products they want, and then within that category, they choose the specific product. And let's let BK be the set of alternatives in nest K. So given a nest, we know which alternatives belong to it, and vice versa. And additionally, each nest has lambda K, which is a dissimilarity parameter representing how similar the alternatives within a nest are to each other. If lambda K is high, that means the alternatives within the nest are very dissimilar, not similar, and they have higher probability of, because they're different, right? So lambda K is a weight, and it's gonna be between 0 and 1. And then again, we want our model to be defined by the choice probability of alternative I given the means, Qi of mu, right? And so that's going to be the probability of choose nest K that alternative I belongs to, and then probability of choosing alternative I given that nest K is chosen. And so, yeah, our first one is probability of choosing nest K. So in the denominator, we'll have the exponentiated weights of all the nests, and then in the numerator, we'll have our nest K specifically, right? So up in the numerator, we have some of the alternatives J that are within BK. So BK is the set of alternatives in nest K, which is where I belongs, right? So we do e to the mu J, and now divided by lambda K, which is our dissimilarity parameter to that nest. And then we take this whole thing and raise it to the power of lambda K at the end. So each weight is being divided by mu K and then after they're all added up, we're raising that whole thing to the power of lambda K. And then the numerator is the sum of this, but not just for nest K, for all the possible nests, right? So let's sum through nests L exists K, our set of possible nests, where we would do sum of alternative J in BL now, the set of alternatives for nest L, e to the mu J over lambda L to the power of lambda L. And then probability choosing I, once we've chosen that nest, is the same as this, right? We still have the dissimilarity parameter. So e to the mu I over lambda K. In our denominator, we're going to have sum of J exists BK because it's already chosen to be K. So we just have that e to the mu J over lambda K. And let's do an example with this one before moving on, right? So let's say alternatives 1, 2, 3, 4 in nest 1, 5, 6 in nest 2, and alternative 7 in nest 3. And let's say that the utility of each choice is the same, which makes it similar, like makes it simpler. I mean, all the products could be uniform, but because the nests are not uniform, they're not all going to have the same probability. The probability depends on which nest, right? So for simplicity, we'll do I0, mu I equals 0 for all I, and then we have to choose the lambdas for each nest. The dissimilarity parameter lambda 1, let's be 0.5, lambda 2, let's be 1, and lambda 3, let's be 0.7. So lambda 2 has the most diversity among the group, so like it has more potential value to the customers. And ui equals 0, so e to the ui equals 1, e to the 0, for all I. And even if we divided that by lambda k, then it would still be true, right? So all these things are just being replaced by 1, and we're left with the lambdas and the exponents. So qi, yeah, again, let's substitute in a specific I. Let's find q1 of, yeah, and our specific mu is given to be 0, right? So q1 equals summation of the alternatives in nest 1. So we have 4 alternatives, 1 plus 1 plus 1 plus 1. Each one has 1. So we're adding up 4 of these guys, which equal 1, and then raising it to the power of lambda 1, right? And then in the denominator, we're going to have that same thing for the nest 1, and then we're going to add nest 2. We're going to have 2 alternatives being raised to the power of lambda 2, and then in nest 3, just 1 alternative to the power of lambda 3. And then we're going to look at this probability over this probability. Well, each of these we just said was 1, so this is 1 over 1 plus 1 plus 1 plus 1. That makes sense. Once you've chosen the nest, the 4 alternatives are all equal utility, so it's just 1/4 probability you get alternative 1, right? So Q1 would be the same as Q2, Q3, Q4. And here, let's just simplify. So we have 4 to the 0.5 over 4 to the 0.5 plus 2 to the 1 plus 1, doesn't matter what power it's raised to, times 1/4. So that gives us 2 plus 2 plus 1 is 5. And then this becomes 4 to the 0.5 on the denominator. So 1 over 10 equals 0.1. And then if we wanted to find Q5, that would be, instead of this one on the top, we would have this second nest on the top, right? So we would have 2 to the lambda 2 over 4 to the lambda 1 plus 2 to the lambda 2 plus 1 times 1 over how many alternatives are in nest 2, which is, or just this number again. Yeah. And then our lambda 2 is 1. Our lambda 1 is 0.5. Yeah, I mean, our denominator is going to be the same as last time, but this numerator is changing, right? And so now it's 2 on top and 2 on bottom, so it's just 1 over that denominator 5 equals 0.2. and then Q7 equals 1 minus 4 times Q1 minus 2 times Q5. So instead of computing it again, we could just say that the sum of all Q's has to be 1. Since they're choice probabilities, Q7 is still in a nest by itself, right? So that would be 1 minus 4 times 0.1 minus 2 times 0.2, which is 0.2. Yeah, I don't know why that took so long. So it's in a nest by itself. It has the same probability as Q5 by coincidence because the dissimilarity parameter is lower. Even though it's in a nest by itself, it is not more likely to be chosen. Yeah, and let's talk more about what is lambda, the dissimilarity parameter. So, like, let's say alternatives 1 and 2 are in nest A, and 3 is in nest B. So if lambda A equals 1, then Q1 equals 2 over 2 to the 1 plus 1, or 2 to the 1 plus, and then times 1/2, because there's 2 alternatives in that group, equals 1/3. With our still mu I equals 0, right? And then each alternative has the same probability independent of the nest, right? So it just so happens, because this is a group by itself, it doesn't matter what the dissimilarity parameter is. It's going to be 1 raised to the power of something, but that's only because we have mu 0, right? But here, the dissimilarity within the group is all the way at 1. So it's equivalent to them not being in a group at all. It's like the nest A has no distinction from nest B because they're completely dissimilar to each other within that nest. But then as lambda A approaches 0, Q1 plus Q2 is going to be this thing, 2 approaching 0, right, plus 1 equals 1/2. So then it's like half the time we choose nest A, half the time we choose nest B. Right, by doing 1 minus, 1/2 is the probability we choose nest B. So now, when the dissimilarity parameter is close to 0, it's like that first choice is very uniform. Like the probability of choosing each nest is about the same. The last big topic we'll talk about is feature-based choice models. So we're keeping the multinomial Logit model, but we're adding features. So the customer's utilities are no longer determined independently for each alternative. Now the utilities are a function of the features of that alternative, right? An alternative has certain characteristics. Let's say the utilities are from this feature vector called x, right? And so ui equals beta tx would be a linear regression on the feature set for some new parameter beta. So x is feature set given for all alternatives, right? And then mu I is the mean utility for alternative I. So each alternative I has a vector x. Right? For multinomial logit, we have qi equals soft max of ui equals beta tx. The parameters beta can be trained from a data set, right? Set of alternatives present in the trained data can be written as sk, right? Because not necessarily all alternatives are present. And then the proportion of observations of choice I when presented with an alternative set sk is like the experienced probability. How out of the total number of times, how many times was that alternative chosen? So let's denote this as yisk. When set sk, or let's say set of alternatives sk is available, what proportion of observations were I? So what percent of the time was I chosen when sk was present, right? And so our beta can be getting from max likelihood estimation, right? So beta hat equals the maximum over beta. So this is saying the beta that we're choosing is the beta that maximizes this function. Or we could even say argmax to denote that we're actually taking the argument, not the actual maximum of the function. Right? So we could sum from k equals 1 to k to denote like the different sets sk, and then sum over the alternatives I that are in that sk. And we're also going to have the zero alternative, which is the case of not buying anything. In the previous steps, like we weren't really making a big deal out of alternative zero. We didn't have any way to treat it differently. But now, alternative zero is not buying any of the products, and so there's no feature set associated with that. So we're always going to be presented with the set of alternatives sk and the zero alternative, which is not making any purchase, and that is independent of the features, right? So that's why isk is the like experience probability for that alternative I, and then we're going to multiply it by the log of q I s k when we input beta. Right, so now qi is a function of beta. We don't have like these mu's given anymore. We're calculating the mu's from beta tx. Right, and it's the log sum of the log probabilities because we're doing the log likelihood. And so that's the same as the arg max over beta of the sum over k sets of alternatives, or basically, you could also think of it as each observation is a different sk. I exists sk or 0 of yi sk times log soft max of beta tx I. So remember in our notation, the softmax I, we have E of beta txi over E of beta txj sum over all j, including the I in the denominator, right? So that's what the softmax function gave us, and that was just how we got the choice probabilities using MNL. Like, this isn't always necessarily concave, so you could use stochastic gradient descent to approximate the local maximum, right? Categorical features of n categories could be included as n indicator variables, like binary variables in X, and then you just have a lot more betas, but they're 0 or 1 values, so it's still decently accurate when you train it, right? And then, like, beyond that, we can look at the mixed Logit model. So beta is the same for all customers and alternatives previously in that homogeneous model. A useful heterogeneous model where you're treating as different customers differently, right? There's some variation within the customers. You can cluster the customers into different groups. Like, it could be based on separate demographic data, which location they went to, etc. Basically, we have some features assigned to each customers, and we can calculate a beta for each group. If the probability of each group is known, then expected value of the choice probability represents the probability for a customer of an unknown group. Then beta for a customer becomes random variable with known distribution g of beta. Like, beta follows g of beta. So that function is telling us, like, how likely each beta is, or what are the different betas that are possible under some PDF, PMF probability function. So Q of I, if this function was discrete, then, and like, our X would also be discrete features. EXP beta T xi over sum from j equals 1 to n of exp beta t x j. So, like, this is the same as softmax, but now we're multiplying g of beta. Or, yeah, not, sorry, earlier I said discrete x. I mean discrete beta, right? Or discrete g of beta specifically. Which we call a PMF, right? In our other case, it's going to be continuous PDF g of beta, right? And there, we're going to integrate over all beta exp beta t xi. Exp is the same as e to the power of exp beta t xj, sum from j equals 1 to n, like all the alternatives, g of beta d beta. In economics, g of beta would also often be assumed to be normal, but then there wouldn't be a closed form integral. You could find it through the normal table, which is found through simulation, or you could, like, evaluate at specific values using an integral calculator, which is basically simulation, right? Like going through a lot of Riemann sums. Yeah, but in our revenue management context, g of beta is often discrete. We have a set of beta that are possible, a set of customer groups that are possible, and we know the probability of each customer group. And that's it for random utility models. Beyond that, there's also rankless models. So instead of defining a parameter for the utilities of each choice, we're just going to non-parametrically compare the choices. So that I'll do in a second video.